Hello. Thank you for the introduction and the opportunity to speak here. This is a joint work with many people, as you can see. It happened mostly when all of us were affiliated with ICOCI Vienna. It is not the case anymore. For example, I'm at Masaryk University in Brno, Czech Republic. Well, this is the first and my least favorite slide of this presentation. So I'm actually very happy that Patricia already kind of established the precedent for these kind of slides. So I'll just say, entanglement is interesting, blah, 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 okay? So, thank you. So, however, we are talking about high dimensional entanglement, so I would like to motivate at least that a little bit. So, if you go beyond qubits, then it turns out that entanglement in higher dimension has many interesting properties and can lead to some serious advantages. For example, in QKD, or higher channel capacities, or in fact higher noise resistance, because you can mix in more white noise to high dimensional entanglement, and it still stays entangled where lower dimensional entanglement wouldn't, right? And well, there's another reason which is more practical. Especially in photonics lab, this high dimensional entanglement sort of comes for free, right? Unlike polarization, other degrees of freedom of photons are naturally high dimensional. So experimentalists keep working with these, and they are getting high dimensional many level entanglement basically for free. Think orbital angular momentum states and or time encoding, right? You can actually measure when the photons arrive. These can get in superposition, therefore you can create very high dimensional state like this. And of course, they would like to have some theory to that as well, right? Now they can create them, what can they do with it? And problem with higher dimensions, however, comes in certification. Because if you have high dimensional entanglement, the task of actually certifying what you have in your lab sort of gets more and more difficult with higher dimensions, right? Think tomography, for example. When you are trying to do a full tomography of a bipartite d-dimensional state, then you need to do d+1 measurement on each side of the state, and especially you need to do this in every combination. So this roughly scales like d squared, and this becomes really impractical for practical purposes for like not even that high of a dimension. So we actually asked if we can do this better. So can we say something about these underlying states with fewer measurements? And it turns out that in fact, yes. So that's the efficient part. What we are doing, our method actually requires only 2 measurement settings on each side, and that is without any dependence on the dimension. So we can do this for any dimension in the same way. And also, we do not assume anything about the underlying state, okay? This is here just because people have done this before, and they have came up with methods that didn't require so many measurements. However, they required some assumptions on the state they were measuring. For example, like perfect correlations in a preferred basis and so on. We don't do that. We don't assume anything about the state. So, just to specify further, we don't trust the source, we don't know what the state is, but we do trust the measurement. So this is device dependent, we fully characterize the measurement we are doing there. And I should also tell you what we actually certify. So this is not a full tomography, so we cannot tell you what the state is exactly. But if you want to learn which state is generated, we instead give you fidelities, okay? We might not give you precisely fidelity to a chosen target state, we just give you some lower bounds. But it turns out they are pretty good, right? This is probably generally for any method. And of course, in high dimensions, it is also interesting to ask how entangled the state is. That means, what is the dimensionality of the entanglement actually? And to do this, we evaluate Schmidt numbers of the state in the setup, okay? If you don't know this, this is actually what I'm gonna introduce next. So this is just a definition of Schmidt numbers. So if you have a pure state, its Schmidt number is simply the number of coefficients in a preferred Schmidt basis. So any d times d dimensional system you can bring to a basis like this, where both of these have the same label, you assign some amplitude to them, and the number of the levels you need here is the Schmidt number. Okay? This can, of course, be extended to mixed states via convex roof construction. The point here is that not every d times d dimensional states has a Schmidt rank of d, which is maximal, right? This is what you would like to see, because that means that the state cannot be represented in lower dimensions, the state and its correlations. So this is what we certify. And this is the starting point. This is a method that was actually published before. I'll list Robert Fickler as the author, but this is actually Markus Huber's method. He was the theorist on this paper, so this is something he done a while back. And this is what it means, okay? So we define these kind of numbers, bk of a target state, which are simply sums of k largest eigenvalues in this Schmidt basis, right? So you take your state, bring it to the Schmidt basis, in which that is nice form I showed you before, and simply for given k starting from 1 to d, you simply sum these eigenvalues. And what this claim says, that if the Schmidt rank of your experimental state rho is smaller than k, then necessarily its fidelity to the target needs to be smaller than this sum. This, of course, can be turned around and turned into a certificate, because if you first measure fidelity and then evaluate all these sums, then the largest k for which is smaller than the measured fidelity is a certificate that the Schmidt number of rho is k, right? This fidelity is inconsistent with Schmidt number lower than k. This is what we are going to be doing in the end. So you might actually now notice that what we need to do is simply to evaluate the fidelity. And we don't exactly do that, but we give some nice lower bounds on it. The advantage of this method, again, is that we just require 2 measurements, while other fidelity measuring methods require more, linearly with d, and we do not assume anything about the experimental state, okay? So let's get started. This is a choice of a target state, right? I write it down in this nice Schmidt basis, and if you write down the fidelity, you just start with the definition, start with rho, you obtain 2 sums like this, and I'll just rename these so you know, so that you actually see there is some structure in it. This is what I called f diagonal and f off diagonal. It's diagonal obviously because it contains only diagonal elements here. This contains some off diagonal elements, and what we in the end are going to do is that these diagonal elements you can evaluate with a single measurement, as you will see soon, very easily. But this is a problem, right? Typically, you need many measurements to give a bound on this part, what the off-diagonal elements look like. And what we actually do later in the proof, technically, is that we split this into 2 sums. One of them can be lower bounded from the diagonal elements, and another one can be evaluated with a second measurement, which we specially actually craft for given target states. So for 2 given target states, these measurements will be different. And of course, I'll explain more in a minute, okay? However, first I need to get into this discussion because we actually, during the review process, had to change the title of this work. It used to be called 2 measurements are sufficient for certifying, and then in the end it got turned into measurements in 2 bases are sufficient for certifying high dimensional entanglement. Turns out measurements means many things to many different people, especially experimentalists were not very happy with the first title because they were asking like, do you really just need to measure 2 photons to get something? I'm like, no, this is not what we mean. So here's the explanation, okay? And this is very much with implementations in mind. So what do you need if you want to implement a D outcome measurement in a lab? Typically, this requires D detectors, right? Because what it means that if particular detector clicks, say this one, it means that the state was, the answer of the outcome is 2, right? I just number them 0 to D minus 1. So this is 2, 1, 0, 3, and 4, okay? For 5 outcomes here. But this is also not so practical in the lab. So what typically happens is actually something different, right? So you only have 1 detector, and instead of doing a projective measurements that genuinely has D outcomes, you're splitting it into several parts. So this measurement would simply measure a projector onto this state, and if the detector clicks, the outcome is 0. But if it doesn't click, it doesn't tell you which of the other outcomes was actually realized. So you don't know. But in turn, if with some assumptions on the stability of the system, you can actually do this measurement, right? You will simply change the projector and do it for all of these single outcome projectors. And here's the difference, right? If you have genuine D outcome measurements, then you need one setting to do a measurement like this, right? You measure something on Alice's side, something on Bob's side, and you're done. However, if you're just simulating this with a single outcome measurement, you need D squared settings because you need to do all the pairs, right? So for each measurement here, you need to try each of these as well. So this is where this D squared number actually pops up. To summarize, so if you do genuine D outcome measurements and the number of outcomes of your measurement is D, then the tomography takes D+1 squared measurement settings, fidelity measurements D+1, our method just requires 2 measurements. However, if you just simulate this with single outcome measurements, this D squared guy appears here everywhere. You just can't get rid of it, okay? So let's go back to this. To reiterate, this is a Schmidt number witness, this is the bound we derive. So what do? Well, I haven't talked much about how to choose this target state. Although, in principle, with this method, you can choose it completely freely. You can just decide what your target state is. In lab, what you actually want to do is a bit more complicated. You need to have a good guess, like what your state probably looks like, right? And this is why we actually put this in a more experimental friendly way, and we define also what you should choose as your target state. And this is a very simple thing, right? So the first measurement is in the standard basis. So this is very easy for experimentalists to tell you what your standard basis is, right? Because, well, what happens in the lab is not that they randomly put some optics elements on the table, they get some clicks and then they try to guess like where the entanglement is, but they do know. They have pretty good idea what they're doing, right? So if they're doing orbital angular momentum, that's your basis, right? They know where to expect the entanglement. So this is what you do. This is actually from the experiment we did. So what you do is measure this basis and simply create these coincidence counts like this, okay? You can see we are simulating 12 outcome measurement with single outcome measurements, and what you expect that if you chose the Schmidt basis correctly, there's going to be clicks only on this diagonal, therefore when the projectors are matched, right? So this is 0, 0, this is 1, 1, this is 2, 2 after some renaming, okay? So you get this and evaluate this. That's the first easy part. However, that's not enough for entanglement, right? So what you do next is calculate these lambdas which define your target state, and it's also very simple. If you interpreted these clicks on the diagonal as probabilities, you simply take square roots to get amplitudes and you're done, right? So this is your target state now. From these clicks here, you find a state that you nominate as a target state, and you're going to measure fidelity to this state. How? Well, you need to define another measurement, and this other measurement critically depends on these lambdas. So after you evaluate these lambdas, you can define the second measurement you're doing, and this is it. Well, it looks a bit complicated, but in fact, if you stare at it for a little longer, you will realize one thing. If you were trying to measure fidelity to the maximally entangled state, all these lambdas would naturally be 1 over square root of d, okay? And if you do this, then they actually all cancel out, and what you get here is just a Fourier basis. So this is the first mutually unbiased basis, the computational basis. And this is actually how this was created. However, we require that this overlap of this new basis with the original basis has this property that pops up in the proof. So you want to cancel as many elements of those sums as possible, and this is what we required. This is why we chose the basis just like this, okay? And what you do then is then measure in this basis, and there's another slight complication. If you take a look and try to evaluate this, this is not an orthonormal basis, right? So these vectors are normalized, but they are not orthogonal generally. And that's why this little c lambda appears here, luckily enough, it's just a correction term which you can evaluate from the measurements in the first basis. However, if you want to do this talk more generally, this simply means that the measurement is not projective anymore and you need to do a POVM. However, in the case we are doing, when we're simulating everything with the projectors only, you don't need to do this. You're measuring single projectors at a time anyway. So this actually doesn't critically need to be orthonormal. You just need to correct here, okay? This is why it's there. So far, so good. Well, and then you do this, okay? Yet again, looks very complicated, but you have all these numbers now, right? This is just a number you obtain from the measurement in the first basis. This is a number you obtain from measurement in second basis. All the lambdas are defined, so you really just plug in numbers into this and it gives you a single number, which is lower bound on your fidelity. That's about it. Why do I have these pink ellipses here? Is just to connect it to the first exposition I gave you. So this is what I called the F diagonal at the beginning. This is what I call the F off diagonal at the beginning. And I also told you that we will lower bound this off diagonal term by some terms that are obtained from the measurement in the first basis. So here they are, right? This one and this one. This is actually the genuine part that you obtain from the second measurement. And now that if you have this fidelity lower bound, you can evaluate this Schmidt number witness and give a Schmidt number of the state you have. And that's almost all from the theory's point of view. Of course, there's more. There's sadly no time to talk about it in detail, but we know, for example, that this is a pretty good lower bound. If your experimental state is pure or a dephased pure state, this inequality here actually becomes equality. So you're as tight as possible. And as I even like, this is the most favorite part, at least for me, of this method, that you can generalize this and add measurements to increase how good your lower bound performs. So if you're not satisfied with your bound with 2 measurements, you can add another measurement and increase slightly better bound. And even better, if your dimension you work with is prime, then if you do d+1 measurements, then this becomes equality for any row. And this is sort of nice because it creates a method that is as good as other fidelity measurement methods in the sense that if you do d+1 measurement, you always obtain a correct fidelity. But in our method, you can actually choose, right? You can choose to stop measuring after some number of measurements because you're happy with the bounds. Turns out you can also generalize this for multipartite states, so you can use very similar methods for Z-like states and so on. And of course, this is just an addendum. If you have fidelity, you can get lower bounds on entanglement of formation as well, just from the fidelity. That's pretty good. Now, the experiment, okay? So we did this theory part, and then it was implemented in a lab. I'm not an experimentalist, so you might not be very happy about this explanation, but yet I'll try my best, okay? So I'm told that this is a fairly typical orbital angular momentum setup, right? So what happens here is that you have a laser that emits blue photons. You simply concentrate them with a telescope into a crystal where the process of spontaneous parametric down conversion sometimes turns some of these blue photons into a pair of red photons. And these red photons have very interesting properties, right? They have orbital angular momentum modes which are entangled, right? And additionally, they are polarized in other ways. So this is a dichroic mirror that filters out the blue photons that you don't need anymore. This is a polarizing beam splitter that separates these 2 red photons so we can measure them separately. SLMs simply are a filter which realize the measurement of these modes. So you have these, this is like the way I imagine it is that it lets through only some very particular states of photons and it reflects the others. And then you just have a simple coincidence logic that gives you the outcomes of the measurements. So this is the press picture, right? These are the holograms on the SLMs, and these are actual intensities of lights that we obtained with cameras in the setup, okay? And as you can see, these are mutually unbiased bases which you would use if your target state was fully entangled, and they are slightly different from the tilted bases we use. Well, kind of beautiful, right? Anyway, this is the actual experiment. What we did, we evaluated fidelities to 2 different states. So first, we chose as a target state this maximal entangled state and really did computational basis and mutually unbiased basis measurements. And in this other experiment, well, additional experiment, we also did the thing I told you. We created these tilted bases, measured them, and by doing so, we could obtain lower bound of a fidelity of our experimental state to this tilted state, because orbital angular momentum state is clearly not fully entangled. These amplitudes are sort of Gaussian. They are not equal. And this is the result we obtained. So we tried this for many different dimensions, 3, 5, 7, and 11. This is the Schmidt number we were able to certify. As you can see, all the way up to 5, we got the full Schmidt rank as possible. In 11, we got 9. The best fidelity we obtained here, and as you also can see, the fidelity to this tilted state is always better than to the maximal entangled state. This 9 is a very important number, because if you count it correctly, there are 8 authors of this paper. And we are very embarrassed to publish this with the same number of, well, witness dimensions than the number of authors, because then we couldn't claim it's efficient. If you need 1 scientist to increase the dimensionality of your entanglement, it's kind of expensive. So actually, and this is true, Mehul redid the whole experiment to obtain better numbers. He got a new laser, so he took the measurements again and was happy to announce that he has a witness of dimensionality 9. And this is a quick summary. So the theory simply says that we can measure fidelity and Schmidt number of an experimental state using only 2 measurement settings, which is much better than previously known methods where this always scaled with D. And in experiment, we actually certified the Schmidt number of 9, which is the highest Schmidt number certified without any assumptions on the state, I think, at the time. Now we can do better. And this is the team. This is a thank you slide. There are a bunch of these people were actually employed on this project. This is the experimentalist Natalia and Mehul. This is Marcus, Nico, and Claude. This is Jelena, our organizer. And this is Jessica. I especially need to thank her because of her I'm here. She applied to this conference with this dog and then couldn't make it in the end. That's why I actually took the opportunity. And additionally, I am using her slides. So really big thank you to Jessica, and I'm ready to take your questions.
Okay, questions?
Hi. I have a question about the summary of results, the experiment one. Yeah. This highest Schmidt number ever certified, do you mean specifically in spatial mode analysis?
No,
or
no. I think this was very general because Marcus knows about these results. He's been involved with this for a long time, and he's author of some of these other papers. And at least he claimed there's also some underlying dirty trick in the claims where they claim they have 100-dimensional entanglement, right? That means there's an assumption on the state. They assume something that might not necessarily be true, but the physical intuition tells them that it should be true.
Okay.
We don't do it. Okay? We just really assume nothing about the underlying state.
Okay, thank you.
Are there any sort of mild assumptions you can make that maybe other people make stronger assumptions? Can you improve like drastically if you made some mild assumptions on the state?
Yeah, sorry, I don't know really. I'm
Okay.
not super up to date with this, and I think yes, because I mean there were papers with claims really just going into
assumptions
dimensional.
Assumptions that you might think are well motivated is what I was
Oh,
thinking.
I think like what we talked about is they really assumed that in a preferred basis they get perfect correlations, right? And this might not necessarily be true, but they assumed it anyway. So there are some tricks to actually, but the motivation is clear, right? You don't really want to do these squared measurements in your experiment. So if you want to certify you have a 100 times 100 entanglement, this would mean 10,000 different measurement settings, and that's just unconceivable.
More questions? Okay, then if not, let's thank the speaker again.